Hi there, and welcome to our lecture on Newton's first and second laws. And this is Force 1 of Unit 6. So our key ideas: what makes an object speed up, slow down, or change directions? What determines how much an object speeds up or slows down? So starting to look at Newton's first law in our first question. So objects will change their state of motion only when we get a net force applied to that object. And we say net force because it's the total forces that are pushing on one side of that object or the other, which allows it to move. And this is Newton's first law. So let me draw a picture here. We have an object sitting on some table or some surface. It's going to stay there, right? So another way that we can say Newton's first law is an object at rest will tend to stay at rest. It's not until that we apply a force, and we'll draw this arrow here to represent that somebody's pushing on this object from this side. It's not until we apply this force, which would be a net force or an applied force, that the object will end up moving or accelerating in the direction opposite, or in the opposite direction. Newton's first law also says that if an object is moving, say we got this round object and it's moving, if you ignore forces of gravity, air resistance, friction, all those things, objects that are moving will want to keep moving. But Newton's first law in the instance of moving objects is hard to really see or observe here on Earth, because we do have things like gravity and air resistance and friction. So objects will tend towards the Earth, and then they'll eventually stop, and it's because there's outside forces that are applied to that object that'll slow it down and bring it to a stop. So we call this, or we can say this way: objects tend to maintain their state of motion, whether it's not moving or moving. Inertia is a term related to an object's mass, and often we say Newton's first law is the law of inertia. Basically, it's how much mass an object has. Or we can also define inertia as the tendency of an object to resist a change in motion unless we have this outside force that's acting on that object, and it's directly related to its mass. The more massive an object is, the more resistance to change it'll have, as opposed to lighter objects. I can push a marble a lot easier than I can push a bowling ball or a boulder or something large like that, maybe a car. So a car would be an example of an object that's a lot more inertia than, say, a marble or a baseball or something. Seat belts and car seats provide protection, and it does so when a car comes to a stop. Your seat belt and the friction between you and the seat provide this unbalanced force backward that basically brings you to a stop as the car stops. So if you're driving along and you slam on the brakes, you have this deceleration that occurs, and when you're sitting in a car, you don't experience or don't feel velocity. You don't feel speed because it's constant. You only feel or can detect acceleration, positive or negative. So when you slam on the brakes, you've got this negative acceleration or deceleration. So that seat belt basically applies that backward force to keep you from slamming into the dashboard. Newton's second law. So what determines how much an object speeds up or slows down? So net force is equal to the mass times acceleration. The unbalanced force on an object determines how much an object speeds up or slows down. And we call this Newton's second law. And Newton's second law is the only three of Newton's three laws that actually has a formula attached to it. So we say net force, or F, is equal to the mass times the acceleration, or F equals ma. Force is measured in newtons. So the unit of F here, or unit of force, is Newton, in honor of Newton. And 1 Newton is equal to kilogram, or 1 kilogram times 1 meter per second squared. Well, mass is measured in kilograms, acceleration is measured in meters per second. So when we're using these really large units, a lot of times it's easier to shorten this down, and that's what they did with the Newton. So instead of writing all of this down, now we can just put in. So 1 Newton is equal to 1 kilogram times 1 meter per second squared. Sometimes it's easier to see Newton's second law written a little differently. So instead of going force equals mass times acceleration, a lot of times what you'll see is, well, an object will accelerate because of the force applied to a mass. So the bigger the mass, the bigger the force has to be to basically have an object experience the same acceleration. So a larger force relative, if we kept the mass constant, we applied a larger force on that same mass, we'd have a greater acceleration as compared to applying a smaller force to the same mass. So we'd have a smaller acceleration. So this form of Newton's second law, this equation here, I think makes a little more sense, and it works out a little bit better, because an object's not going to accelerate unless you apply a force. Well, if an object's accelerating, it obviously has mass, so there's some force that's causing it to accelerate. So I mean, they're basically saying the same thing, but I think it's easier to look at it as A equals F divided by m, or acceleration equals some force applied to an object, and we use m to signify mass as our object. Alright, so for equal forces, a larger mass will accelerate less. So if we apply the same force to a bigger object, it's not going to accelerate or move as quickly. So if we look at the football players here pushing on the sled, well, the sled that has a smaller mass, but the same force, same two guys are pushing on it, will have a greater acceleration. So we can push this thing a lot farther, a lot faster, as compared to the right side here. Because we have more mass, now we've got 3 extra guys on here, we've got an extra weight. So these guys pushing with the same force, the sled's not going to move or accelerate as fast as before. So then if we have equal masses, if we apply a greater force, we then get a greater acceleration. So let's say we've got this car, we've got one person pushing, well, they're only going to apply so much force. Well, if we have 2 more people, so we have 3 people pushing on the same car, we're going to have more force and we'll have more acceleration. So let's look at a math skill, a math example really quick. So you got a zookeeper that's going to lift a stretcher that holds a sedated lion. The total mass of the lion and the stretcher is 175 kilograms. The upward acceleration of the lion and the stretcher is 0.657 meters per second. So what force is needed to produce this acceleration of the lion? So we're given mass as 175 kilograms, given acceleration as 0.657 meters per second squared, and we want to know what the force is. So this one's not too terribly difficult if we look at what look at our equation for Newton's second law. Force equals mass times acceleration, or F equals ma. We're going to insert what we know, and since we're already in kilograms, meters per second, there's no conversions that are needed. If this were grams, we would have to convert to kilograms first. and then we can multiply. So if this were grams, we would divide by 1,000 to get kilograms. So what we get is 115 kilograms times meters per second squared, and that kilograms times meter per second squared simplifies into newtons. And then we could say Newton's second law can be stated as follows. The acceleration of an object is proportional to the net force on an object and inversely proportional to an object's mass. And this goes back to what I said, A equals F over m. So this is what this is saying, just acceleration equals force divided by the mass. There we go. Thanks for listening.